a faculty at Tennessee State University. So the talk is Moving Target Defense, Lessons from Hackers. So the basis of the talk is what can we learn from the botnet evolution since the late 90s till ongoing, right? And so how can our defense mechanisms can learn from the trials and tribulations of the botnets, and taking a page from the hackers, taking a page from botnets. So again, most of the stuff is academic. Some of that has made its way into R&D. Some of it is operational. But major defense techniques that I'm going to talk about is academic. But the botnet stuff is out in the wild, so that's known for everybody. And so the lesson from this talk is what can we learn from that and how we can make our defense systems more robust. So that will be the focus, and I'll talk about some ongoing work that my lab is working on. So what is the problem? So most of us know the cyber warfare is asymmetric. You try to plug one hole, another one opens up, and so that's a losing battle. So if you look at the defense techniques, right, so there are so many paradigms and lines of thought. Most of them are static, black box, and set and forget, which, as we all know, is not very effective. So why are they not effective? Again, the asymmetric conundrum. Can we then take a leaf out of the hacker's playbook or the botnet's playbook where instead of fortifying every asset, make the systems move to the defender's advantage, right? So it's easier said than done, right? What do you mean systems move? You're talking about apps, you're talking about compilers, you're talking about OS, you're talking about operating systems, networks. So there are a lot of things that you could diversify and move, but that presents a complexity challenge. And how do you balance the trade-off between perceived security advantage and performance that you incur if you try to diversify everything? So that's what we'll talk about. So again, in a nutshell, what is MTD? It is coming up with mechanisms that are diverse. Now, diversity can be at the app, can be at the system, can be at the network. Continually shift, being agile, and be dynamic. So in essence, if you present a static configuration, then you're a lame duck, right? So it's very easy to attack you. So what can you do so that your configuration is not static? It's almost like with any professional sports, and you can't defeat a good player. You can just make them work harder, right? So that's the premise over here. Can we make the adversary work harder? And with that, buy some time while you're protecting your system. So again, not a new concept. The military has used it. This has been going on since the art of war. If you have read the book, folks are using military a lot. So this is an example of a dogfight where you're trying to figure out what type of tactics you can employ to evade the attacker. So this is a air combat type of activity. I don't know how many of you have watched this episode from Star Trek. This was a shield nutation type of concept. Again, trying to figure out whether you can randomize frequency, random intervals, and comms guys, RF guys use this a lot. Randomize your spectrums. This is work going on in cognitive radio networking. Just keep on randomizing your frequencies and hop around at different intervals. Again, in this particular episode, I don't know how many of you remember this. It didn't work out very well because the attacker was freaking good, so it didn't. And so when a game is set up that way, you're going to lose. So hopefully that's not the case all the time. So coming to MTD in terms of systems, the work is going on at all these levels. How can you randomize your program? For instance, how many of you use JavaScript or have used JavaScript? So if you know, in JavaScript, if you want to do any type of cross-script injection attack, you get your get document by element, get document by ID, right? So everybody knows that. What if you randomize that? What if it's not exactly the same instruction set, but it's some randomized version of it, right? So then you're making it a tad difficult for the attacker to quickly launch the cross-site attack. Same thing at the host and the cloud and the network mobile. So you can identify how to diversify the different systems and networks. So again, as I mentioned, some of this is operational. Some of the work at the instruction set is operational already. Intel and AMD have done that. But a lot of other work is still in the research phase. The reason why it's research is because the challenges that I just mentioned: when to move, where to move, and how to move. And finally, what is the cost? I think the cost is not clear, right? So you can come with a nice technique, but then users and customers want to know that what is the cost of you moving my asset just because you feel that there's early detection of an attack? What is the performance trade-off as it pertains to you in live user activity? So some of the initial work that is going on. So if you start at the very low level, instruction set randomization. So how many of you have ever written a buffer overflow code? So if you know, with buffer overflow, the basic concept is inject your code, right? Many different ways to inject your code, but ultimately the concept is I got to make my code run on your system. So if I get to do that, I get root access, and all that you own is mine. How you get into it is not the point, right? The point is that you can attack it or you can execute your code. But what if we just randomize the instruction set where your code doesn't work, where your code crashes? So you're assuming that the instruction set is known to you. What if that is not known to you? What if the instruction set has been randomized? So this is the origins are from biology on genetic mutation, but can we do that with instruction set? So making sure the programming language is unknown to attackers. And of course, there's a trade-off, right? Now, all your binaries in your system have to be randomized because they have to be, making sure that they don't follow the standard instruction set, but a modified instruction set. So it's a trade-off to make sure. Just to prevent an attacker, you've got to make all the legitimate binaries translated randomized during installation. So that's the trade-off you got to take into account. Software diversity. The same type of deal where you're trying to either the variable reordering, randomization system call, library entry point, or insertion of knobs to make the programs functionally equivalent, but internally different variants. Okay, so this is a good example of the App Store. So you download an app from the App Store, and the resultant binary will be different, different variants. But functionally, they're all the same, right? So with all the different phones, you will notice that functionally they all operate the same, but you have multi-compiler that will make sure that they are not the same binary. So if you have a worm that is trying to propagate, it's not going to propagate because of the fact that the binaries are different. And this is just taking to the next level, where you diversify the compiler itself and making it tad difficult for any worms to propagate. Internet service diversity. So this is an example that I was talking about, that JavaScript attack, right? So you can make sure that your SQL injection and cross-site scripting don't work because you randomize your SQL queries, your JavaScript, and why not your Perl scripts too, right? Why do your Perl scripts and all those keywords and all those function calls be the same? You can either use encryption or you can use an XORing mechanism to just diversify the keywords, diversify the function call names. And I don't have the sample code here, but you can imagine the Perl code that you've written can be translated to a slightly a different variant by varying your encryption key seed, and you'll get a different type of code. Moving further with network diversity, right? So to make sure that folks who are trying to do network wireless penetration, network penetration type of activities, how to make sure they don't work. So again, your IP addresses and your routing tables, trying to make it harder to do. So your network recon and your OSN network fingerprinting will not be successful. So that was pretty much the state of the art that is going on. What I want to spend a little bit more time is the botnet influence, right? And so most of you know what a botnet is: network computers that are set up to conduct different activities. They have a command and control center that are responsible. And so the requirements are, I need to know my command and control technologies. I need to be able to evade detectability, have to be able to monitor the botnet activities, do some disruption, figure out future command and control technologies, and just recover from the damage. This is evolution, but I have slides over here. So real quick, I'll do this overview in a couple of minutes. It all started with IRC-based botnets. So most of us who have been at IRC, it started with using IRC channels, and through IRC channels, you would be able to communicate with your CNC command and control. But it was easy to take down, right? These are hard-coded IRC channels. So it didn't take time. 5 years tops, this didn't pan out. I think around 2002, it was time to go. And so since 2002, we have gone into slightly sophisticated, still centralized botnets. Okay, we still haven't gone into distributed. We're still centralized, where we are now figuring out a way where can we have different IP addresses. So there was a big analysis done where they found out that using fast flux, where how many of you know fast flux? So fast flux is a technique where you can have a DNS record for your domain name, but the time to live value is very short, maybe a few minutes, a few seconds. So you're trying to go through a lot of same domain name, but different IP addresses in a short period of time. So you're just going through multiple IP addresses, and which is not typical for any normal domain. So that's your fast flux. But that's easy to catch too. You're rotating your IP addresses, but you got the same domain name. You can catch that easy too. So then they came up with a technique to rotate your domain names, right? So they came up with, okay, I'll make sure the domain names are now the same. So they changed the domain names by, I think, every week they had a different domain name attached to the top level domain, and just very deterministic schemes, because that's the premise, right? So whatever technique you have, whatever heuristic you have, if it's deterministic, it's easy to get hold of you. So again, the domain name flux, you can see the numbers are 50,000 domains every day. So again, sophisticated, but centralized, even though they had some sort of dynamism in there. The challenge is that the obfuscation was very weak, right? You're trying to obfuscate yourself by changing IP addresses. That's not working. You're trying to obfuscate yourself by changing a domain name. That's not working, because the domain generation algorithm is deterministic. So it's easy to catch you. Whatever technique you come up with, I'm going to change the domain name by adding the week of the day or week of the year or whatever you want to come up with. They're all easy to catch because they are still deterministic. So the maturation started happening around about 2008, where we finally, from 97 to 2008, took 11 years to go to decentralized botnets. So now we are talking about, I don't know how many of you know how Skype works. So Skype works with this concept. I don't know who borrowed ideas from whom, but traditionally the idea is a tiered architecture. So you're using a centralized and a P2P architecture. Okay, so you have your spammers, which are behind the nets, and you have your repeaters, which are basically your bot masters, which are connecting your spammers. And that's what a Skype works. You have got your relay nodes, and then you have your end users who want to talk to each other. And so this was the beginning of a more sophisticated botnet, which is harder to crack, because now they are also using encrypted communications, not revealing themselves too much, not exposing each other to everything else. So you had to do very intelligent network traffic analysis. You can still guess estimate their architecture. So that's what was done, similar to Skype, right? If you want to know how Skype works, you got to do traffic analysis to figure out how the architecture is set up. So the work has been done, but not much is known still, because a lot of the communication between the spammers and repeaters goes through encrypted channels. So that is hybrid, and then you have complete P2P botnet, which is also similar, but it's so hard to infiltrate the CNC architecture. So external traffic analysis works, but not good enough. So that's an example of a Valentine virus, which was propagated by one of these botnets. So that is the summary. The last two botnets that I showed you are by far the most robust architectures. And so that's where we need to, for folks who are looking at defense mechanisms based on botnet, that's the way to go, to find out your botnet topology. So this is a slide that summarizes everything. So you got your hierarchical, hybrid, replicating network, then the different authentication mechanisms, certificate, password, encryption, the control mechanism, either you're going to do a SQL injection, obfuscate a CNC, so on and so forth, your communication protocol, and then your rallying mechanism. So your rallying mechanism is including as many bots as possible. So are you going to go through IP-based, DNS-based, DNS fast flux, so on and so forth. So what is your rallying mechanism to include as many bots as possible? So that's the entire evolution. So what did we learn? We learned that in 1997 to 2015 and onwards, the progression from static to dynamicity happened this way. Started with IRC channels, port numbers, IP addresses, and DNS names. So that's where we are. And the CNC mechanisms have evolved from static to dynamic, and there will be multiple attack vectors, and the poison prevention to make sure that the P2P list doesn't get poisoned, and the index is not poisoned. That's also something we learned. So I wanted to use cloud computing as a system where some of the botnet ideas can be applied. So cloud computing has a similar type of structure. It's distributed, has on-demand access to computing, storage, and network resources. So with MTD, you want to do system and network virtualization to achieve the required diversity. And because you have a lot of redundant computing, storage, and network resources, you can pull this off. So again, one of the attacks is on cloud is depriving access. So you can, and this happened with Xbox, Netflix. You could not get hold of the services because there was a DOS attack. And similarly, most of the attacks on cloud are based on lack of availability. So this is a couple of examples of attacks. You got your Xbox, you got a Netflix attack, which of course is dependent on Amazon. Dropbox down there also depends on Amazon for its infrastructure. So how are these two related? So the cloud and botnet, they both have the same infrastructure, they're distributed. They are supposed to be controlled by a single entity. And both of them, have the availability requirement. That's the same thing in botnets, right? You can't take down the entire botnet. How can a botnet survive? You can take down some of them, but not every one of them. And that's what cloud services can learn from that, right? So you can take down some of the cloud resources, but not all of them. So you won't lose the access to the service entirely. So to put in a nutshell, what are the polymorphism capabilities? Your memory randomization, your code obfuscation, your encryption, and your agility, right? How can you randomize your source, your IP, your domain name? And those are the things that the cloud infrastructure needs to base its design on. So some of the mechanisms, more details. So the network topology, polymorphism, which comes from the dynamic CNC architecture. So understanding the bot's command and control structure, which right now is a combination of hybrid, centralized, and P2P, and even just P2P, and understanding that architecture and imbibing some of those principles in your systems might lead to a very resilient structure. The scheduling based on diversity, and again I showed you examples of diversity in OS, diversity in system, and the whole goal is to have a continuously shifting attack surface. So that is the holy grail, right? It's so hard to pull this off. To have a continuously, it's very easy for me to state it out here, but to pull it off, to have the shifting attack surface at your app, at your system, at your network, and all seamlessly working together will take a lot of time, but it's a line of thought to see whether that can make it difficult for the attackers to get into it. So I just, in interest of time, I'll keep this very short. So some of the work that I'm doing in my lab. So this is one of the work that we just completed. So the work was to migrate your apps across virtual machines, and to do that across heterogeneous virtual machines. So to make sure the same vulnerability does not get propagated, right? So if it's the same vulnerability, if you have a heterogeneous virtual machine replication, not a homogeneous, heterogeneous virtual machine application, so you're moving your app across different hypervisors, or you're moving your app across different guest OSs for the same hypervisor, whatever the case may be. So that was a technique we developed, and that pertains to a cloud-based MTD, where you have randomized replicas of your systems, right? And the randomized replicas are based on different hypervisors or different same guest OS or different hypervisors, or different guest OS but same hypervisor. So that is your heterogeneity. So the same vulnerability will not get propagated. Again, we did this thing, but some of the things we didn't do was a live user activity going on, and what is the performance impact. So we haven't done that. And so the performance can be an issue depending on if the user activity is live or not live. And that's some of the future work that we need to do, but it was a good start for us to look into it. And just more details on how we did this, so you can definitely look me up to see some of the work we did here. We were trying to also do the same thing for network diversity, to present your network configuration into a different type of graphical structure, so you know all your different attack paths, and you can diversify your network system. So again, some preliminary results. So one on virtual machine, one on network diversity. And then we also wanted to see the cost of attack, so cost of moving target defense. So this was the work we did to figure out what would be the cost. You're moving your virtual machines just because you're anticipating an attack, but what would be the cost to the other activities on the network, right? So you have other network activities, and they have their own quality of service. So how do you balance the two? Just because you're trying to evade an attack by moving your apps between different virtual machines, how would that affect the quality of service of, so what is the cost of MTD? So we had a cost model to look at the cost of moving your application. So that would be a good incentive, right? So you could have an incentive mechanism with users, right? So if there's some cost incurred in moving the user's VMs, then the user could be incentivized. So I'm about to end, so this is my summary. So again, MTD as a strategy to learn from botnets, some of the techniques. I showed you examples of instruction level diversity, software level diversity, compiler level diversity, network level diversity, and to be able to pull that off will be very good across all the layers. And with mobility, social networking, and we haven't even looked into those areas, how mobility and social networking and the randomness in MTD plays into this. And moving forward, what will be the attacks on the MTD scheme itself, right? And hopefully, if these policies are in place, then we can make some headway into security metrics. That's all I had. Thank you for your time. Any questions?